So basically what we have discussed so far is we discussed how to analyze the amplifier circuits. We have first in any amplifier circuit that contains DC bias and AC signals, we have to first analyze the DC first, determining the operating point and determine the operating point, the DC bias point, which includes the base current, the DC base current, the DC collector current, the DC emitter current. Once we determine and solve the DC circuit or the DC analysis, we can calculate the parameters, the AC parameters GM, R pi, RE, RO, which we explained in the previous video, and all of them they depend on the DC values of IC, I base, IE, okay, in addition to some constants, early voltage or the threshold voltage VT. So we'll be able to calculate these parameters for the small signal model. And once we calculate these parameters, we are now ready to do the AC analysis. We are ready to analyze our AC circuit, calculate the gains that we are going to obtain, calculate input resistances, output resistance for the AC circuit. Okay, for the circuit that deals with our signal that we want to amplify, like our voice. If we want to amplify our voice signal, then this is the AC signal. We study the circuit, we calculate the gains, how much our voice will be amplified, what's the input resistance that our voice, our AC signal will see, what is the output resistance that the output signal will see, and so on. Okay? And then we analyze the AC circuit by removing all DC sources, deactivate the DC sources. If you have a voltage source, how to deactivate a voltage source? You make it zero or short circuit. Voltage source, to deactivate it, to make it zero. If you have a DC current source, you deactivate it by making open circuit, right? So a voltage source is deactivated by making it short circuit. A current source is deactivated by replacing it with an open circuit. And then we replace our transistor, our bipolar junction transistor, with one of the small signal models, either the pi model or the T model. You can use any of them. Both of them are supposed to give you exactly the same solution. However, for some cases, using the pi model is easier. For some other cases, using the T model is easier to analyze. And you will get this by experience, which model to use with which circuit. And we'll see that from the examples that we are going to solve. Okay? So you replace the bipolar junction transistor with the, one of the models, either the pi or the T model, and then you analyze the circuit to determine the required quantities, which is usually the required quantities are, you calculate the gain, you calculate the input resistance, the output resistance, and so on. Okay? So this is how we solve amplifier circuit. DC first, calculate the parameters of the AC, then replace the transistor with the model, do the analysis and calculate. When you replace the transistor with the model, of course, you have to deactivate the DC sources, replace the transistor with the model, do the analysis for the AC circuit, calculate all the gains and input resistors, output resistors. Okay? Let me see the screen turned off here. So let's move now to the amplifier families. As we have seen from the mechanism of amplification, we saw that we do changes to the voltage VBE, and this will lead to changes in the big changes in the collector current or the emitter current, and these changes in the collector current or the emitter current will lead that the voltage VCE will be changed with big changes. So the changes in the VCE will be amplified. So you do small changes in VBE, very small changes in VBE, this will lead to big changes in VCE. Why is that? Because there is a gain between I base and IC. When I base changes with very small changes, these changes will be multiplied by beta in IC. IC will change with big changes. When IC changes with big changes multiplied by beta, it will cause that VCE will change with big changes. This is how the amplification happens. So basically, the input, the small signal, your small changes will go to VBE. You need to cause change to VBE, and what you will get big change to VCE. So your input basically will be change to VBE, output change to VCE. In order to change VBE, you have two options. Either you keep the base constant and you change the emitter, you change VE, or you keep the emitter constant and you change the base. So in order to change VBE, you have two options. Either you change the base and you keep the emitter constant, or you change the emitter and you keep the base constant. In both cases, you can change VBE. For the output, in order to take the big change of the output, in order to take the output of your circuit, you can, or you have two options. Either you keep the emitter fixed and you take the change as changed in the collector. You take the change, your output, you take it from the collector and you keep the emitter constant, common, okay? Or you fix the collector and you take your output from the emitter. So you have two options for the input, you have two options for the output. For the input, either you fix the E and you change the base, or you fix the base and you change the E. This, in both cases, you will change VB. The output will be changing VCE. So how to take the output terminal? The output terminal can be taken from the collector if you fix the emitter. So all the changes will appear on the collector. If you fix the emitter, for example, you connect the emitter to ground, all the changes will appear on VCE. Or you connect the collector to ground, and in this case, you take your output from the emitter. So we have two options here, two options here. How many different options total? How many combinations can we get? Think about it. I hear some of you saying 4, because we have 2 for the input, 2 for the output. But I'm telling you, this is not correct. This is not accurate. We have only 3 options here. Why? Because the input has 2 options. The input has 2 options. Either you put the input, you connect your input at the base or the emitter. Right? And the output has also 2 options. Either you take the output from the collector or you take it from the emitter. So how many total options? You can connect the input to the base and take the output from the collector. You can connect the input to the emitter and take the output from the collector. You can connect the input to the base and you take the output from the emitter. But the fourth case here is not valid. Why? Because you cannot connect the input and the output to the same terminal. You cannot connect the input and the output, both of them, to the emitter. So the fourth case here, this is not valid, and you have only 3 options. These 3 options will result in 3 amplifier families with 3 different characteristics and 3 different properties. The 3 different amplifier families, the first one, when you connect your input to the base and you connect or you take your output from the collector, this is called common emitter. Why common emitter? Because when the input is connected to the base, the output is taken from the emitter, from the collector, then the emitter, the third terminal, we call it the common terminal. It's like the terminal that will be connected towards the ground. So when the input is connected to the base, the output is to the collector, the third terminal, the emitter, is called common. So that's why we call this amplifier family, we call it common emitter. When you connect the input to the base and you take the output from the emitter, the third terminal, which is the collector, is called common. So we call this family common collector amplifier. When you connect the input to the emitter and the output from the collector, we call this family common base. Common base amplifiers. So we have 3 amplifier families: common emitter, common base, common collector. Usually, how to know it? Look at the input and the output. The third terminal will be the common terminal. So we have 3 amplifier families, which are the common emitter, common base, common collector. In any amplifier circuit, before we end this video, in any amplifier circuit, we will notice that we have some capacitors. These capacitors can be classified into 2 types of capacitors. This is an example of an amplifier circuit. We have some capacitors that we put before the input and the output. So this is our input. We usually connect it to the amplifier through a capacitor. Also the output is usually connected to the amplifier through a capacitor. These capacitors, they are classified as something called coupling capacitors. Coupling capacitor. While there is another type of capacitors that will appear sometimes in our circuits, like this capacitor, which will be connected parallel to some resistors. This is called bypass capacitors. What is the benefit of the coupling capacitors that are used between the input and the amplifier, between the amplifier and the output? These are called coupling capacitors. What are the benefits of this? Let's think about this. When we design our amplifier circuit, this is our amplifier circuit, we choose a certain bias point, a certain DC operating point, certain bias points, right? We design it based on a certain bias point. So we choose the resistors, we choose everything, all the parameters inside our amplifier so that it operates at a certain bias point. Now imagine that you are going to connect your amplifier to a load. What will happen? Now you are connecting your circuit to a resistance. This resistance can change all the calculations that you did, right? It can change your bias point completely. You designed at this bias point, but once you connect it to a resistance, the calculations, all the currents, all the voltages can be changed, and the bias point is going to change. So now you designed on something on a certain bias point, and when you connected it, it is operating now on a different bias point. Same thing can happen when you connect your circuit to an input source or a previous stage. Usually the input comes from a previous stage because we don't use a single stage amplifier. Usually we use many stages. So the input to this stage, it comes from a previous amplifier circuit and so on. Previous amplifier, stage, and so on. So we have multi-stage. So the input here comes from a previous stage. So when you connect your amplifier to a previous stage, again the circuit has changed and the bias point also has changed. So how to prevent this? How to prevent that the DC bias point changes? They connect something called coupling capacitors. So these coupling capacitors, with respect to the DC, we know that with respect to the DC, a capacitor is an open circuit. So with respect to the DC, for the DC bias point, if you look at this capacitor, you will see an open circuit. If you look at this capacitor, you will see an open circuit. While with respect to the AC, and this is what is important for the amplification, with respect to the AC, these capacitors will be on. And for simplicity here, we'll consider that for AC, the capacitors will be short circuit. So with respect to the AC, these capacitors will be short circuit. With respect to the DC, they will be open circuit. So with respect to the DC bias point, it will not be affected by connecting RL here or connecting a previous stage here. The bias point will stay the same because it sees open circuit here, open circuit here. With respect to the AC signal that we will amplify, it will go directly to the load without any problem. It will see a short circuit and it will be amplified and it will go to the load, like your speaker here or whatever. So here, this is the benefit of the coupling capacitor, is that when you connect a load or you connect a previous stage or a next stage, the bias point is not going to change. It will remain as it is because the capacitors represent open circuit. While for the AC signal, the capacitors have no effect because approximately they will see the capacitors as short circuit. What about the bypass capacitor? Sometimes you will see this capacitor connected across a certain resistor in our amplifier circuit. It's called bypass capacitor. Why do we need this? In some cases, we need this resistor to appear in the DC analysis, while we need it to disappear in the AC. So some resistors, it's useful to us in the DC, but we need to get rid of them in the AC analysis. For example, to increase the gain. For example, we need to get rid of this resistor in order to increase the gain. But we need it in the DC. So what they do is, they connect a capacitor in parallel to it. For the DC, this capacitor will be open circuit, so the resistor will exist. The resistor will be there, because the capacitor will be open circuit with respect to the DC. For the AC, the capacitor will be approximately short circuit. So this resistor will be short circuited and it will disappear. It's like you can remove it because it's short circuited, right? So here we could, through the bypass capacitor, we can control that some resistors will appear in the DC analysis to control our bias point or do whatever we want, and they will disappear in the AC also for some benefits that we will have in the AC analysis, like increasing the gain or whatever. So using the bypass capacitors, they are useful to keep some resistors during the DC and remove them during the AC automatically. Okay, this is the benefit of bypass capacitors, and we already talked about the coupling capacitors before. So this is what we will see in any amplifier circuit that we'll study. In the next video, we'll start the different amplifier families, the 3 amplifier families, and we are going to solve some examples on each of them, and we'll see the difference in properties and characteristics of each of them. See you in the next video.